Hey everybody, it's finally time that we move beyond our polynomial functions in terms of taking derivatives. So every single function that we've been using as a shortcut right now, we've been using power rule, and it's been polynomials. I guess we've had radicals and some fraction functions as well, some rational functions. But at this point, we need to get some more into our tool belt. So this is 3.5, derivative of trig functions. So grab your notebook and also grab your foldable. We're gonna need that in a minute. And let's title this 3.5 derivatives of trig functions in your notebook. As always, you can always rewind and go back and replay something, or to pause if I'm asking you to solve a problem, which I will in a couple minutes. So let's dive in. All right, so let's start with the sine function. So I've got my sine function from -2 pi to 2 pi, and I would like to know what the graph of the derivative looks like. Now, some of you might already have an idea, but let's do it a little bit more systematically. So let's graph some of the slopes, or at least figure out what some of the slopes are. Let me make a table here. And I'm going to go through, and at -pi, I guess I'm going negative pi to pi, not -2 pi to 2 pi. So at -pi, what does it look like the slope of the tangent line would be right there? I don't know exactly what it is. It's definitely not 0. So it's some kind of a negative slope. And again, what we'll wind up seeing soon is that, we'll find out, is that it is a slope of -1. It's a perfect diagonal. So I'm going to now, on the same graph, I'm going to plot a point at -1. So that's my first point on my derivative graph. All right, let's go to the next point. -pi/2. So what's the slope at -pi/2? Well, that should be pretty easy. That's a big fat 0, horizontal tangent line. So I'm going to plot a point at 0 right there. Third, now I go to 0. Well, if I said the 1 back at -pi was -1, this looks like this is going to be a +1. So that's a +1 slope. Keep going. pi/2, 0. Pi, -1. And again, I'm plotting each point as I go along. So the green dots here, they're representing the derivative at select values. Now again, there's a lot of other values in between. So do you think this is going to look, this looks like an upside down absolute value function. Is that what the derivative is going to look like? Well, probably not, because the way that these slopes are changing, this is not quadratic, remember, this is sinusoidal, so the derivative is not going to be a line, but it's more than likely that the graph is going to have some kind of a curve to it. Well, if I connect those dots, what does it look like? Well, yeah, it is the cosine function. The cosine function. The sine function relates opposite to hypotenuse on a right triangle. Cosine's relating adjacent to hypotenuse on a right triangle. But now we see that every single coordinate on the cosine curve is the slope of the sine curve. That is huge. We now have our first derivative of trig function. The derivative of sine of x equals cosine of x. That's worthy of putting in a little door on our foldable. So on the outside, d dx of sine of x, and on the inside, cosine of x. Now, there's a chance we might run out of doors here on our foldable. So if we do, then we'll just make sure that we get and make another foldable. You can make one too at home if you got some paper. Otherwise, we can make one when you come in. All right, that's kind of exciting. Derivative of sine of x is cosine of x. All the points on the sine function's slopes wind up graphing and becoming the cosine function. Think about that. Maybe play around with that thought beyond what we're doing in this video. So let's do cosine. So I invite you to pause right now, maybe make a table again from -pi to pi of all those values, selected values. You're gonna probably see some same slopes again, and then plot those points and see what graph you get. Going through and plotting my points. After I get my slopes, and connecting those points. Is this what you thought? You might have thought it might have been the sine function, but it's not. It's actually a reflection of the sine function. So it's the negative sine function. The derivative of the cosine function is the negative sine function. That's worthy of going on our foldable. So you're doing that and putting that on, just think about what would the derivative of negative sine be? Well, remember, negative sine is just negative 1 times sine. What do we do with constants out in front of functions? Nothing. So the derivative of negative sine of x is going to be negative cosine of x. But what's the derivative of negative cosine of x? No, it's going to be sine of x, because I'll have a double negative, negative cosine. We'll draw this out here in a minute when I get my pad of paper here. So awesome, 2 derivatives. So what do we do about tangent? Now tangent, I could look at the graph, but looking at the graph, there's all kinds of like weird asymptotes in the tangent function. And some of the slopes get really steep. How about, is there a more systematic way of us doing that now that I know the derivative of the sine and the cosine? Well, yeah. I can take the derivative of the tangent by using the quotient rule. Because if I'm taking the derivative of the tangent, isn't that the same thing as the derivative of sine divided by cosine? Huh. And if I know now the derivatives of sines and cosines, and I also know the quotient rule, well, then I should be able to find the derivative of tangent. So pause right now, go and do the quotient rule on sine divided by cosine. See if you can simplify it and see what it simplifies to. And then come back and check to see what I'm doing. So here's low d high minus high d low, all over the square of what's below. Now we're not going to leave it like that. Let's do some simplifying. Well, what happens up in the numerator? I'm going to get cosine squared plus a sine squared, double negatives, all over cosine squared. Hey, anybody see something from last year? I know you had that big sheet from Mrs. Miller and all of those trig identities, but there is a couple that we should remember. Cosine squared plus sine squared. Yep, it's 1. It's a Pythagorean identity. And 1 over cosine squared, well, that's an identity too. What's 1 divided by cosine? 1 divided by cosine is the secant. So it's secant squared. And ta-da, we now know that the derivative of tangent of x is secant squared of x. Now, what the secant squared graph looks like, I'm not quite sure. You're welcome to go and graph it on your calculator, 1 divided by cosine squared. But again, the secant function, remember those functions with all those u's? They have definitely some asymptotic behavior, lots of discontinuities. Well, those are probably going to be at the same places where the tangent function has its discontinuities as well. Well, so I've got 1, 2, 3. 3 of them so far. So I've got derivative of sine, cosine, and tangent. Well, there's more trig functions we know. We know the reciprocal trig functions. So what about cosecant? What about cosecant? Well, let's see if we can do cosecant here. I'm going to switch to my document cam. I should, let's see. Let me go back here. To my document cam. Here we go. So I'm going to do cosecant. Well, cosecant is just 1 over sine. When 1 over sine, I could do a quotient rule with it. So if you want to pause, try it, see if you can simplify it, and see what I do. So low d high, it's going to be 0, minus high d low, all over the square of what's below. So it looks like I simplified a negative cosine over sine squared. Well, that's not real pretty. Now, what do I have inside of here? There's a cosine and a sine, and then there's an extra sine on the bottom in the denominator. Well, do we know what those are? What's 1 divided by sine? And that's cosecant. What's cosine over sine? And that's cotangent. And don't forget, there was a negative there. So therefore, the derivative of the cosecant function is negative cosecant x cotangent x. So let's jump back in onto, let's see if I can do this. I hope that worked when I was doing that. You know what? I don't know if that did. I think maybe it did do it. All right. Sorry, I'm going back here. All right, so let's get all of our lists of things here. So here are some of the others, and we could do the same thing. Derivative of cotangent, we could do as cosine over sine. That's going to turn out to be negative cosecant squared. Down at the bottom, I did cosecant of x is negative cosecant cotangent. And then secant of x is secant tangent. So at this point, I have 6 trig derivatives. Again, these are going to go in your foldable. If we run out of room on the foldable, at least get them into your notebook for now. We can always grab it and make a new foldable. You're welcome to make a new one at home, but we can make one in class as well. Okay, I'm going to go on to 2 examples. So you can pause me now if you keep writing. So what I'd like you to do is now put them into use. So pause the video here in a second, and I want you to perform our basic operations because we see a product rule and a quotient rule going on with these, and utilizing your new trig derivatives as you're doing them. So pause me now and then try these 2 problems, and then I'll show you what the solutions are. All right, so using product rule, 1d2 plus 2d1 for the first one. We're not going to bother simplifying these. You could play around with identities, but that's not necessary. And the second one should be low d high minus high d low all over the square of what's below. So at this point, we now know some trig derivatives, and we can utilize them in a couple different situations. So at this point, make sure you go and practice some of the problems that I have on the page.